This video will be an introduction to vectors in an arbitrary number of dimensions. So a vector, well, let's first define what a scalar quantity is. So a scalar is a quantity that only has magnitude. So it does not have any direction, it is simply a value with a given magnitude. Vectors, by contrast, are quantities with both magnitude and direction. So the question is, how do we represent both the magnitude and the direction of a vector? Well, some vectors that we're comfortable with and familiar with are vectors in a 3D Cartesian environment. So you have an x-axis, a y-axis, a z-axis, much as you do in the 3D world as we experience it. And we have some vector A coming off of the origin and extending to some point there. So we're fairly confident that it has some length, the length from where it starts to where it ends, and it has some direction in terms of x, y, and z. So how can we represent this? So we have the vector A, represented by this little vector symbol over the top of it, is equal to, we can also represent it as the letter A with a single line underneath it, indicating it's a rank 1 tensor. We'll more on that in later videos. We could also represent it as a bold letter A, indicating that it is a vector quantity. So that equals, well, we have these three component vectors, x, y, and z, that are what we're going to call basis vectors. So we're going to express A in terms of the basis vectors x, y, and z. And when we talk about 3D Cartesian points, implicitly this is what we've always been doing, but we may not have realized it formally. So the vector A is equal to its component in the x direction times the x unit vector, a length 1 in the direction x, plus the direction plus its magnitude in y times the y unit vector, length 1 in the direction y, plus the component in the z direction, length in z times a unit vector in the z direction. So we're representing these x, y, and z hat. These are called basis vectors, and in this case they have unit length and they are orthogonal to one another. They are independent of one another. They go in independent directions. In 3 dimensions or in 2 dimensions, we could say that they all form 90-degree angles to one another, but that language gets more complicated when we think about more dimensions than 3. So for now, what we'll say is that they are unit length and orthogonal. So given that we have these unit length and orthogonal basis vectors, what we can then say for our vector A is we can represent it as this column vector here. So it's kind of a curvy type of bracket here, and then it has AX, AY, and AZ, the three components that represent it in the X, Y, and Z dimensions for our vector. Now we're used to these components being some real number, so anything from negative infinity to infinity, but in general they can be complex as well, so they could have some imaginary component as well. We're not as familiar with that, but it becomes very useful to us in quantum mechanics to be able to represent vectors that are complex in an arbitrary number of dimensions. Okay, so that's in 3 dimensions, the type of vector that we're used to. So what about in an arbitrary number of dimensions? So in general, we'll represent some vector A by a column vector here, where we have its coefficients in n dimensions. So each of these is called an element. We have an element of the vector. It has n elements, and that means it is in n dimensions. It is an n-dimensional vector. Okay, so what are some properties of vectors that we want to define now in order for us to be able to use them for some useful things? Okay, well, first thing we want to do is define the dot product of 2 vectors. So we have A and B. We represent that by A dot B. So what does that equal to? So we might have seen this in Calculus 3 in terms of what unit vectors are going to be for their dot products. But now instead of summing over 3 dimensions, we're going to sum over n dimensions, and that's going to be the ith component of A times the ith component of B. So for B, find its first component multiplied times A's first component, then add A2 times B2 plus A3 times B3, etc., all the way down to AN times BN. So this only works if A and B have the same number of elements and they have the same number of dimensions. Okay, and that, as I said, is called a dot product. You might also see that called an inner product or a scalar product, but dot product would be the most common name, perhaps. All right, next up, we want to note some special properties due to the dot product. So if the dot product of A and B is equal to 0, then we say that A and B are orthogonal. Okay, so that's another property of that vectors can have if they are orthogonal to one another. So when we said x, y, and z are orthogonal to each other, these unit vectors, that means that their dot products would be 0. And we can see this because in this type of representation, x would be 1, 0, 0, and z hat would be 0, 0, 1. So there's no point where they both have a non-zero value. So those vectors are going to be orthogonal to one another. Okay, so that's orthogonal. That's the first part. What about this unit length part? How do we get the length of a vector? So that comes from the dot product with itself. So A dot A is equal to the sum from I equals 1 to n of the ith component squared, and that is equal to the magnitude of A squared. So that magnitude so the magnitude of A is going to equal the dot product with itself to the 1/2 power. And you might notice that this is basically equivalent to kind of a Pythagorean theorem type representation of it. If it was in xyz, this would be x squared plus y squared plus z squared square root. So it's the Pythagorean theorem in an arbitrary number of dimensions. So that's the magnitude of our vector. So we're representing the direction of it with its dot products with various other vectors, and its magnitude by its dot product with itself. All right, so we have these components of these vectors. So let's take a look more at these component vectors. So these are x, y, z in 3 dimensions, but what are they going to be in arbitrary dimensions? So we're going to have in an arbitrary dimension are going to be our basis vectors in some arbitrary number of dimensions. So an arbitrary unit vector in whatever n dimensions that we have. So what is A dot B when we express them in terms of these unit vectors? So remember, A is equal to, we'll have A is equal to the sum, that's not a good sum, sum I equals 1 to n of AI EI. Similarly, B is equal to the sum, let's say a different sum, j equals 1 to n B sub j E sub j. All right, so then the dot product of those two, A dot B, is going to equal a sum from I equals 1 to n, sum from j equals 1 to n of AI times B sub j E hat I dot E hat j. So we'll notice this looks quite similar to our expression for the dot product originally, but what has to be true in order for this to be the case? This has to be that the only value that contributes here is going to be B sub I. The only value is going to contribute is when j equals I. So that means that this dot, but we know that these values aren't necessarily 0, so we know these values all have to be 0 except for when j equals I. And when they do, they're unit vectors, so their magnitude has to be 1. So that means that E hat I dot E hat j is equal to a symbol we're going to define as the Kronecker delta. So this Kronecker delta, delta ij, equals 1 if I equals j, and it equals 0 if I is not equal to j. So this is a statement that our basis set is both orthogonal and normalized. It's orthogonal because it's 0 when they're not equal to one another. Their dot product is 0 when they're not the same. When they are the same, their dot product is 1, meaning their magnitude is 1. Square root of 1 is 1. So they are normalized. And that means that the basis vectors for our vectors are orthonormal in this case. Okay, so that is the orthonormality of the basis set. What about these ax, ay, and az? How would we get those individual components there for some arbitrary vector? So if we look carefully at our definitions here, you might be able to notice that if we take the vector a and we dot it with the vector e hat I, we're going to get the value ai as a result. So our components here, our component of a vector in a given dimension is going to be the dot product of our vector with that particular unit vector which represents that dimension. So we can get those coefficients if we know how to calculate the dot product of our given vector with that given unit vector that represents that dimension. Don't quite know how we're going to fit the rest of this in here, but let's go ahead and try. All right, so some other facts about vectors that we can fit in here. So if we have the transpose of a vector, indicated by this superscript t to the right side of it, that is going to be, so our regular vector is what we call a column vector there. The transpose of our vector is going to be a row vector. So that'll be a1, a2, dot, 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 an in a row. Then the adjoint of a vector, which is like a little cross symbol, not quite a T, the horizontal bracket's a little bit higher than a standard T. This is the transpose and conjugate. So this is equal to AT star, which is taking the complex conjugate of all of those components of the vectors, dot, 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 up to an star. Okay, how do we add vectors together? What do those components look like? So if we have don't need the underline if I have the vector symbol. So if we have a plus b I, so the ith component of a plus b is just ai plus bi. So whenever you add two vectors together, you just add the appropriate components together in the appropriate dimensions. So it'd be ax plus bx, ay plus by, az plus bz. And the analogous result in many dimensions. Okay, what if we multiply a vector by a scalar? So what if we have alpha, which is a scalar, times a vector alpha times a vector a? What are the components of that? Well, there you just multiply each component by alpha. So I'm going to have ai there. So alpha times a would be alpha ax, alpha ay, alpha az, etc. for however many dimensions our particular vector has. Okay, and then in terms of matrix multiplication, which we'll discuss in the next video, so a row vector times a column vector will give us a scalar back, which we'll discuss more in matrix multiplication, but I'll write down the notation here. So A dot B is going to be equal to A transpose times B. So in matrix notation, if we treat this as vectors, A transpose times B is equal to the dot product. You're summing up, multiplying each of the individual components together as you go for the vector. Because that's how matrix multiplications work. We have rows times columns, and we get a single number back out. And then finally, our last result that we're going to be interested in is if we have the complex conjugate of A dotted with B, which we'll be interested in a lot in things like quantum mechanics, we have the adjoint of A times B in terms of the type of matrix multiplication if we treat these as kind of one-dimensional matrices. So that'll become more clear and more important after the next video on matrices, but this is the basis. This is the basics of vectors, how vectors work in n dimensions. It's the same kind of intuition we have about working with them in 3 dimensions, just extended to a little bit more formal terminology.